let's continue with our structure theory for finite abelian groups. So I want to give a summary of the entire theorem that we are looking at in these three lectures in the first few minutes. Okay, so let M be a finite abelian group. So let M be a finite abelian group. We fix that. So whenever I write M, it is to be understood that M is a finite abelian group. Then what is its structure? That's the question. And we saw that a naive answer was that M is okay. So let me put that as a question. What is the structure of M? What is the structure of M? That's the question. And the naive answer is that M is a finite direct sum of cyclic groups. Of course, those are finite too, of finite cyclic groups. Okay. Well, that was our first answer, but we sort of refined it yesterday, and we said, so let me put it in a different color, finite cyclic groups, and you can assume that these are of prime power order. Okay, given any finite abelian group, you can always write it as a finite direct sum of cyclic groups of prime power order. Okay, now we haven't proved this fully yet, but never mind the proof. Let us try to understand this, what this means first, by means of a few examples. Okay, so and even derive from this the final theorem that we want. Okay, so let's take an example. So given this, so here is an example. So M could be, what it means is Z mod 2Z to the power 5 or something, prime power orders. So it's Z mod 2 square Z to the some power plus Z mod 2 cubed Z to the some power, etc. Right? Maybe this doesn't occur, so let me put a 0 here, let me put a 3 here, and maybe that's all for the 2 powers, but maybe you can continue with Z mod 3Z, maybe 3Z doesn't occur at all, maybe 3 square Z occurs 5 times, everything is a direct sum. Okay, maybe that's all for 3 powers of 3, and maybe there is a power of some prime, let's say 23, right? 23 to the power. So this occurs, say, 15 times, right? And so which means 5, 7, 11, 13, etc. Those prime powers don't occur. And then you have, say, 41 Z to whatever power, let's say 2021, for example. So it's something like this. Okay, so this is so how far we have gotten, but then using this we can do something else, right? So let us So we have these, you can arrange them like so. Arrange them like so. For example, so let P1, P2, etc. be the primes, right? And you have Z mod P1, Z to some power, right? So some power there, Z mod P1 square Z to the some power, and so on, some power. So this is some power, which I'm not writing, and so on, right? And it's a finite direct sum. So it's Z mod, some of these could be zero, right? P1 to the K1 Z, say, to the some power, etc. And then here also you can for the, so this is 2 and this is 3, and for each one of them you have a decomposition like this. So what I can do is assume that, take the longest one. Okay, so here 2, arrange them is in decreasing order, meaning here, so this is in so what I mean is, for example, here 2 cubed is there, here 3 square, here 41, here 23, right? So for each power, each prime power, okay. So let's take this example and do it. Sorry, maybe I should have done it. And I'm not saying it very well, because this is much easier to write and understand than it is to express technically in correct notation. So for example, for this, I want to rearrange this and think of it like this. Okay. Let's write T2 cubed Z first. And what was the power we took? We took it to the power 3. Okay. Okay. 3. Okay. Okay. At this 0 I will omit. This is 0th power. And you have Z mod 2Z to the 5. Okay. Okay. That's it for 2. Okay. Now let's write for 3. There is a single thing, Z mod 3 square Z, and to the power and to the power 5. Okay. Right, that's it for 3. Okay. Now Z mod 23Z to the power 15, just a single one. So there is a direct sum here. So Z mod 23Z to the power 15. And then there was Z mod 41Z to the power 2020. Okay, I made these numbers up. Okay. Now what you can do is, take the largest one and group them like this. Okay, and the next ones, group them. So here there is only one, this. So when you group them like this, well, okay, let me okay, rather, okay, I should not group it like this, but okay, so this is 2021 times. Okay, I need to do that. Sorry, I didn't group it very well. So Z mod 23Z, this is 15 times. 15 times. Okay, and Z mod 3 square Z is 5 times. 5 times. And Z, okay, let's write, so Z mod 2 cubed Z, direct sum Z mod 2 cubed Z, direct sum Z mod 2 cubed Z, plus, or direct sum, z mod 2 to 2z, this occurs 5 times. Now let us group them. So this you can group. If you do group them, observe that 41, 23, 3 square and 2 cubed are relatively prime pairwise. So by the Chinese remainder theorem, we see that this is actually their isomorphic to their product. So what you have is z 41 times 23 times 3 square times 2 cubed z. Okay, so let us forget this. Let's forget this z. Okay, let me not keep writing this. Let me just keep track of the number below, and that number is 41 times 23 times 3 square times 2 cubed. Okay. Okay, now let's look at the second one, right? So this is again 43 times 20, this repeats. Okay, this repeats. How many times does it repeat? Well, it can repeat 3 times because this is there. So this is 3 times. And then look at after 3 things, what do you have? Here you continue to have 41. Here you continue to have 23. Here you continue, still there is a 3 square, and here there is a z mod 2z. So what you get is 41 times 23 times 3 square times 2. And how many times do I get that? Well, up to the time that this, so see, beyond the, so this will stop after 5 times. So this repeats 2 times. Okay. Then now let's go on. Now I have finished 5 of them, right? And how many are left here? These are 3, and these are 2 of those. So I have 3 more left here, right? So for each of them, I will get these 23, 41, and 2. So I have 41 times 23 times 2. This repeats 3 times. Right? Because out of these 5, these 3 are gone, that is this 3. 2 more are gone here. So remaining are 3. Okay? Okay. Now how many are gone? Now 3 times 2 times 3, that is 3 plus 2 plus 3, 8 is gone. So here I have 7 more left, and what you will get is 41 times, so then you have 41 times 23 alone. This repeats. Out of these 15 times, 8 are gone here. So this is 7 times. Okay. And finally, 41 itself repeats. How many times? Well, it appears 2021 times, but 15 times is already gone. So it's 2006 times. Okay. Now that's the analysis that we get. But now observe the following. Now you see these numbers, right? This is 41. So this is, you can write this as a sum of cyclic groups. How many cyclic groups? So there are, it's a direct sum of 2021 cyclic groups. Okay, and what are those? This number, this is the order of that cyclic group that repeats 3 times. So Z mod 41, 23, 3 square, 2 cubed, Z, whatever that number is. Okay, let's not bother what it is. But what power does it occur to? That occurs 3 times. So this occurs 3 times. So let me write it like this. This means you repeat this cyclic group 3 times. Okay. Now you have this group 41, 23, 3 square, 2, Z. Okay. Now this repeats 2 times. Okay. Plus Z by 41, 23 times 2 Z. Now this repeats 3 times. Z by 41 times 23 repeats 7 times. And then it's only Z mod 41Z. And how many times does it repeat? Well, out of 2021 times, there are 15 times in which we've already accounted for differently. So this is 2006 times. So there you go. 2006 plus 7 is 2013 plus 3, 2016 plus 2, 2018 plus 3, 2021. That's how many different cyclic groups are there in this decomposition. And what is the property now? Observe from the way we have constructed these, and this works in general, because you're going to write the prime powers for any given prime in descending order and group the highest ones together, right? And you know, if you want, justified, all the highest ones are justified. So so here 41 to the power 1, 23 to the power 1, 3 square, and 2 cube. These are the, observe that these are the highest powers of the primes that occur, right? Well, there is 2 cubed, and there is just 2. We are taking 2 cubed here, right? So this repeats. So the first time you take it, I have this. The next time, okay, once you and you repeat the process. So you take the highest powers, right? And then you remove them, right? And you collect them to form a single cyclic group by Chinese remainder theorem, and you remove that and take the next highest ones and you group them, etc. And why in this process, we may run out of, for example, after 5 times, I'll run out of powers of 3. Doesn't matter. Then I just think of it as 3 power 0. For example, here, that 3 power 0, here it is 3 power 0, here it's also 2 power 0. We've also run out after the powers of 2. So what this shows is that what this shows is our final theorem. So from what we have just stated to this final theorem is just a matter of regrouping the, writing these prime power, combining some of these prime power order cyclic groups into some other cyclic groups, but with the property that, so now here is the property, right? So given a finite abelian group M, there exists integers d1 dividing, okay, so how should I do? D1 is the highest one, but that comes at the end. So D1, D2, dk such that, so these are positive integers greater than or equal to 2 such that dk divides dk minus 1 divides dk minus 2 and so on up to d1 such that such that and m M is Z mod D1Z, direct sum Z mod D2Z, and so on Z mod D sub K Z. Okay. Moreover, these D are unique. Okay. So what we have done is if we grant this statement, right? If we grant this statement here, that M is a finite direct sum of finite cyclic groups of prime power order, then to get to the existence of this such numbers d1, d2, dk, it is not very difficult, because this is exactly what I have demonstrated by means of an example. But you can do this in general, and that's what I was trying to write out here. It's harder to write out than it is to understand. It sometimes happens that we perfectly understand what's going on, and in any given case we know how to do it, except if you want to develop notation and write it very precisely in general, that can be difficult. Okay, so this is one of those cases. So I will not try to bother to introduce the correct notation, etc. It becomes too cumbersome. But we know how to do this. You take the highest powers, justify them, and then combine them by the Chinese remainder theorem. That will give you D1. Then look for the next highest powers. That will give you D2, etc. So what are the D1, D2, dk in this example? Well, D1 is this number. D2 is also this number. D3 is also this number. D4 is this. D5 is also this, and that's because this occurs twice. And then D6 is this. D6, D7, D8 is this number. So let's write it out in the above example. I'm not sure I chose a particularly nice example. In the above example, K, the number of these is 2021, because there are 2021 factors, right? Okay. Now, 2006 of them, the bottom ones, are 41, right? So D1, D2, up to D2006, all these are 41. So this condition that D1 divides D2, everything is satisfied very trivially. Everything is 41. So, okay. So this equality could hold in this. We allow that. And then, right, then it is 41 into 23. That occurs 7 times. So D2007 is 41 into 23. And then it is the same thing up to another 7 months. So that should be D2013. This is also 41 times 23. Okay. And then 2014 is this one. 2014 equal to D 2015 equal to 2016, and this is 41 into 23 into 2, and then here, so that divides D 2017 equal to D 2018, and those two are 41. Now 41 into 23 into 3 square into 2, and finally that divides the 9, this 20 and equal to 21, and these 3 are equal to 41 times 23 times 3 square into 2 cube. Observe that each time I'm increasing the prime powers. Okay, maybe there will be, when I move from the lower one to the higher one, there may be a new prime that may start appearing as well. For example, when I move from 2016 to 2017, the power 3 comes up, the prime 3 comes up with some power. And it could keep, the power could increase, as in this case. Here from 2018, there is a 2. 2019 also has a 2, but here the power of 2 is 1, here the power of 2 is 3. Okay? Right. Okay. So you could ask, okay, that I hope that gives you the idea of how to prove this existence of this. And that's just, actually, we haven't done much at all today. We just have used the Chinese remainder theorem and combined it with the statement that we can assume that the cyclic groups are of prime power order, and then just arranged it so that these numbers come out. D1. Okay. Now there is also the uniqueness to be proved. Okay. So how do we show uniqueness? So, for example, if you had this dk minus 1, dk minus 2. So suppose somebody said, look, this abelian group is the sum of cyclic groups this way, and I write d1 divides d2 divides dk in some way. And somebody else comes along and says, look, you can also write it as dk prime, dk minus, another set of integers which have the same property, and you take their direct sum. And why shouldn't m be equal to that, right? So, for example, we have this standard, very elementary example. Z mod 6z is also written as z mod 2z plus z mod 3z. Now, if we write z mod, which of these corresponds to this? For example, if we are claiming uniqueness, well, this does not have the property that the 2 does not divide 3. So this is not the right thing. So if I want to express this group in this way, I'll have to write it like this. Okay? So the question now is, why are these unique? Okay, so let me just let me not give you an entire proof, but I'll give you an indication of how you might start thinking about it. Observe that, look at the annihilator of M, right? The annihilator of M is an ideal in Z. It's a non-zero ideal in Z. We already saw right at the very beginning that if you have a finite abelian group, then there is a positive integer that kills it, that kills the entire module. And therefore, you can look, when you look at the annihilator of M, which is an ideal, that's a non-zero ideal, and being an ideal in Z, it is some there is a positive integer that generates that ideal, unique positive integer that generates that ideal. Okay, and if you look here and see what is that annihilator, then you see immediately that it must be D1, the highest of these. So this D1 intrinsically is, you can read off D1 from M by saying, let me just look at the annihilator of M. And whatever that, and look, that's an ideal, that's going to be an ideal. And whatever that generator of that is my D1. Okay? If I make that statement, then so then somebody else writing this as coming up with these numbers will be forced to write this this biggest number in their list must be the same as the biggest number in your list, right? Okay, and so on. Next, you can think about how do you characterize D2 or dk, etc. Right? How could you go about saying how do I find what D2 is given M, right? I want a description of D2 in terms of M, so that I can say that that is uniquely determined, etc. So far we've got D1. So the claim is D1 is just comes out to be the annihilator of M. It's the generator of the annihilator of M. Okay. So right now let's just wonder about this, and I will. Maybe we'll get an idea in the next proof that we are going to do, of how we might think of getting D2, D3, etc. intrinsically from N, so that we know that these are uniquely determined. Okay. Now where are we? Okay, so let us go back to the. Let me review what we did yesterday before I start doing something new today. And what we did yesterday was that we proved the Chinese remainder theorem. That's one of the things that we did. And using this, we did what is called the primary decomposition of a finite abelian group. Okay, and from this, we concluded that the primary decomposition says that M, a finite abelian group, is the direct sum of PIM. This was the notation we used, where PI runs over PI is a prime. Okay, that is PI belongs to the set 2, 3, 5, 7, etc. Okay, now this looks like an infinite sum, but this is actually only a finite sum because M is finite. Okay, and what is this PIM? We had several descriptions of this PIM. So the way we did it was you took this D to be some integer. So let D be such that D times M is 0. Write D. Of course, you can be very efficient and take this to be precisely the annihilator. You could take it to be some multiple of the annihilator as well, no problem. But if you wanted to be very efficient, then you could take this to be precisely the annihilator. Write this D as P1 to the R1, P2 to the R2, and Pk to the Rk. Okay, and then this M, because dm kills it, is a modulo over z mod dz. The z structure descends to z mod dz because d kills M. But then this, by Chinese remainder theorem, is P1 to the R1 cross Z, P1 to the R1 Z, Pk to the Rk. Okay, and so you have these elements EI. You have these elements E1, Ek in here with the property that they're idempotents, which means EI square is equal to EI. And they are orthogonal idempotents in the sense that EI, Ej equal to 0. And also they are sort of complete in the sense that 1 can be written as E1 plus E2 plus Ek. Okay, now what are these EIs? The E1 is just the integer, the integer here that maps to 1, 0, 0, 0, 0. That's what E1 is. More generally, EI is the integer in Z mod dz which maps here to 0, 0, 0, 1 in the ith place, and everything else is 0. Okay. Then what is our PIM? PIM is just EIM. That's it. So this was the primary component, and we had seen, or at least mentioned, two other ways of looking at it. So let me just mention one of them here again, namely that PIM is the CELO PI subgroup of M. Okay, so this is equal to the CELO PI subgroup of M. The CELO PI subgroup of M, as we observed last time, is unique because M is abelian and therefore every subgroup is normal. So the CELO PI subgroup, they are all conjugate by Celo's theorem, as we know. And since it is every subgroup is normal, it follows that there is a unique CELO PI subgroup, and that is this PI of M. Okay. So we are reduced to understanding the structure of PIM. And what PIM is, from this description, it follows that this is a module over Z mod P I to the Riz. In other words, it's an abelian group which is scaled by some power Pi. Okay. Now the question is, what is the structure of such a module? Okay. So we are down asking what is the structure of a finite Z mod Pi to the Ri Z. Okay. Now, once again, let's look at some examples and then guess what this might be. So what we are driving towards is the proof of this statement, right? We are saying that M is a finite direct sum of finite cyclic groups of prime power order. Okay, so what we have done by using the Chinese remainder theorem is that we've decomposed this as a finite direct sum of the primary components. Now if we just look at these primary components and show that each one of them is a finite direct sum of cyclic groups of prime power order, then we'll be done. Okay, so what do we guess here? Well, we observe that there are certain obvious modules here, right? There are Z mod P1Z, Z mod P1 square Z, up to Z mod Pi to the Ri minus 1 Z, or even Pi to the Ri Z. Okay? Let us simplify rotation and call this Pi equal to P. Okay, so from now onwards, so this is Pi, this is Pi. I will stop writing Pi, but write only P. Okay. So with that convention, what we have is Z mod Pz, Z mod P square Z, etc., up to Z mod P to the Rz. Okay, these are the possible. So let me also write Ri is equal to R. Okay, so these are some obvious modules. of z mod p to the r. Okay? And I can further take the direct sum. So I can take z mod pz to the some power, say k, okay, let's call it L1 or something, right? First power L1, z mod p square z to the power L2, dot, 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 z mod prz to the power Lr. Okay, sometimes I write this direct sum L1, sometimes I write just this power. Both are the same. There's no difference. Okay, and then the claim is that so the claim is that this is it, that the isomorphism classes of finite z mod p to the r z modules are indexed by tuples R1, sorry, L1, LR of non-negative integers. So this is one obvious construction that we have made. Namely, I choose some L1, L2, LR. It's possible that all of them are 0, in which case we just get the 0 module. Okay? That is included. Otherwise, I choose some L1, L2, LR. Right? They should be non-negative. That's the only restriction. And then form this direct sum. Right? And that gives me a finite Z mod PR sub module. And the claim is that these are all. And every finite Z mod PR Z module is actually one of these. Right? So this is the claim. Okay? All these are non-isomorphic to one another, and this is it. Every finite Z mod PR Z module is one of these. Is there a question? I'll be very happy to answer if there's a question. So the question, let's try to understand how we might want to prove this statement, that given a module, so let's ask ourselves the question, given a finite module, a finite Z mod PRZ module, M, how do we get L1 to LR? This is the question. Okay? So let's ask that question. How am I going to, given an arbitrary finite module, how am I going to get L1 to LR? Okay? To understand this, let us take a simple example and do it. So let's put P is equal to, say, 5 or something. And let me actually take a module which looks like, so let me just take some module like Z mod 5Z, right, to the 3, Z mod 5 square Z to the 2 or something like this. Let me just take a module like this, call this M. Okay, M is already presented to me like this. Okay, so since this is a problem. Let me just try to understand it in a case where I know what the answer is. The answer should be, so this is just 3, 2, right? L1 is 3, L2 is 2, right? That's the case. But let us ask ourselves, how, how am I going to extract this? I'm given somehow, I'm not given the left-hand side. I'm only given M as a module. Okay, I have this module. How am I going to extract these numbers? Okay, let's ask ourselves that question. And one thing here to observe is the following. Ideally, we should have played with this a little bit to understand precisely what is going on, but we don't have the luxury of time. So let me tell you right away what the idea is. So you observe that 5 square times m is 0. Right? So that's like p to the r kills this m. Obviously, because that's a finite p to the r module. Okay? Now, what is p to the r here? Well, r could be 2, r could be something larger, r could be 10. Okay? So these are, as long as r is bigger than or equal to 2, this example still holds, meaning it is still a valid example. Okay? So 5 square times m is 0. And let's look at 5 times m. Right? And then there is m. So these are submodules like this. 5m is a submodule of m, and 5 square m is a submodule of 5. And you can form these quotients, m mod 5m and 5m mod 5 square m. The advantage of doing this is that these two are modules over z mod 5z, but z mod 5z is a field. So instead of calling them modules, you can call them vector spaces. Right? So you can look at these become vector spaces over z mod 5z. And I can ask myself, what is the dimension of this and what's the dimension of this? Right? And these are finite because everything M is a finite object, right? It's a finite as a set to begin with. So definitely the dimension of these objects as vector spaces over this field Z mod 5Z is going to be finite. So let's ask ourselves, what is the dimension of, so let's ask ourselves, dimension of, let me call this K. Let's call this K. Let's put this equal to K. And the question is, what is dimension of K over K of M mod 5M and dimension over K of 5M mod 5 square. Okay. Now, if you look at M mod 5M, right? So what is 5M? 5M here, this part it is actually 0. Right? Here it is 5z modulo 5 square z, right? Which is isomorphic to, you can think of that as z modulo 5z. Okay, so what you will get here is 5. This corresponds to this 3 and this 2 here. This 3 and this 2 together give you this 5. And what is 5m by 5 square m? Right? When I take 5m, all this part becomes 0. and here you will get 5m by 5 square m will give you 2. This is 2. So this is 5. So let me write it in a different color. This is 5 and this is 2. So what I'm suggesting is these numbers are obtained as follows. So you look at these. Finally, how do we? So we are trying to answer this question: how do we get L1 through LR? Okay, and the answer to that question is as follows. It's not directly. I'm not getting L1 through LR, but I'm getting. So let me illustrate what is happening in this example. So I'm getting not 3 and 2. I'm getting 5 and 2. Where this 5 represents this, the sum of 3 and 2, and then this 2. So what the numbers that we will get will be LR, LR plus LR minus 1, and so on up to L1 plus dot 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 LR. Okay, so we will recover these numbers as follows, and then from these numbers I can of course recover L1 through LR by just subtracting from here. For example, if I subtract LR from this, I get LR minus 1. If I subtract this from this, this from the next one here, then I get LR minus 2, and so on. Okay, so how am I going to get these numbers? These are precisely dimensions of, the answer is, these are dimensions of M mod PM, and this is the dimension of PR minus 1M by PR. Okay, so the claim that we need to prove is that here, so what this suggests is, this example suggests, is that is the following statement, and it's, so here is what it says: dimension of P, I take some I minus 1M by IM, and look at the next number, Pi minus 2M by Pi minus 1M. Okay, this number is going to be bigger than or equal to this one. And let's ask, so that's what this is saying. So this M mod PM is going to be bigger than the dimension of PM by P square M, and that is going to be bigger than the dimension of P square M by P cubed M, and that's going to be bigger than or equal to the dimension of PR minus 1M by PR. Okay, the reason why this is true, so this is from this example, we can sort of guess this, that this is happening. And now we are forced to ask ourselves, okay, this is happening, but why is this? How do we prove such a thing? And so here is how we can do this. So here is the claim. So here is a proof of this. Suppose, so I want to say this is bigger than this. So I take a basis of this. Remember, all these are modules over Z mod Pset, which is a field, and therefore these are vector spaces over that field, and they are finite dimensional. Suppose I take a basis of this over Z mod Pset, and how can I write a basis? Every element here is P to the I minus 1M. So suppose M1, M, okay, I don't want to write K again. So MS maybe in M are such that P to the I minus 1 M1 P to the I minus 1 ms form a basis. Okay. This, you should look at this as pi minus 1m by pim. Okay. So I should be putting the bars over these, but let's avoid it. Okay. So this I'm not putting the bars to keep the notation simple. Okay, such that these form Z mod Pz basis of pi minus 1m by pim. Okay, then p to the I minus 2 m1, p to the I minus 2 ms, and now I look at them in this notation. P to the I minus 2m by p to the I minus 1m. Or we cannot say they form a basis of this. If they did, I would have equality here, for example. That's not what I'm claiming. But I'm claiming that they are linearly independent. So they can be completed to a basis, and this means that this is what we want to do. So this is the claim. So this is the claim. Okay, and we need to prove this claim. If we do this claim, then this is done. Okay? How do we prove this? Well, once we observe it, then it's rather trivial to see. Okay? Suppose not. Suppose there is a linear dependence relation among these. Okay, suppose, okay. So proof of the claim. Let's proceed by contradiction. So suppose there is a linear, non-trivial linear combination, non-trivial linear dependence relation among these elements. So that suppose, let's say lambda 1, pi minus 2m1, lambda s, pi minus 2ms equal to 0. Right? Which means that this belongs to, okay, now let me just lift it and write this pi minus 1m. So I'm doing a lot of abuse of notation here. Now, so I should have written bars here. Maybe there should be, okay, maybe there should be bars here. So let me continue to write 0 here. Okay. Then I can just sort of multiply this by p. So there is a map from, so the observation here is, there is a, okay, let's just multiply this by p and see that, so this means this is 0 in here, then just multiply this by p and I will come down to this being 0 here, but that's not, so let's do this, multiply by p. To get lambda 1, to get the following, Lambda 1 p to the I minus 1 m1 plus lambda s p to the I minus 1 ms is equal to 0. So this is 0 in, so when I say this 0, I mean in p to the I minus 1m by p to the I. Okay, this seems a bit strange because how am I just allowed to multiply by p? Well, there is a map here, pi minus 2p by pi minus 1p. If I can multiply by p, and there is a map that goes to here. And this is a Z mod Pz linear map. Okay. And well, this is okay. This is an onto map. Okay, you can say it this way also. Okay, so this is an onto map, and therefore this dimension is bigger than this dimension. Maybe that's much simpler than doing what I did. Okay, but anyway, so this inequality holds. So what we get, so the idea how the to answer now, going back to this, how do I recover this L1 through LR? I do it as follows. I look at demand. So here is what I do. I look at dimension of M by PM. Okay, call it, what should I call it? Let's call it Q1. Right? Dimension of M by PM by P square M. Let's call it Q2, and so on. Dimension of P to the R minus 1M by PRM. Let's call it QR. Okay, and then what we have is this is bigger than or equal to this, is bigger than or equal to this, is bigger than or equal to this, and then we set this QR is equal to LR, right? And this must be equal to LR minus 1 plus LR. So I put LR minus 1 is equal to, so I define it to be QR minus 1 minus QR, and LR minus 2 to be QR minus 2 minus QR minus 3. Sorry, R minus 1. Okay, and so on. L1 is equal to Q1 minus Q2. And this is how I recover. Okay, so this is, of course, there is now, this is only an idea, right? So we given M, I have some guess about how to get these L1 through LR. Now it remains to prove that this how to say that M is actually equal to this, right? I have just extracted these numbers as these dimensions, but why is this isomorphic here? That's the question, right? Okay, for that, what you can do is the following. Sorry, that doesn't work very well. Let me create a new page. Yeah, that's good. Okay. So now how do we prove? So we've given M. So what we have done is given M, we've produced L1, LR, right? By this process. So what is Li is what? Dimension of Mi. Sorry. Let's do this again here. Li is dimension of pi minus 1m by pim minus the dimension of pim by pi plus 1. This is what Li is. Okay. That's how we have defined it. Now, why should given this, why should M be isomorphic? Now we are saying it is Z mod Pz to the L1 direct sum dot 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 L Z mod PRZ to the L. Why is this? Okay. Now this is another interesting problem, and so one way of solving this, perhaps there are various ways of looking at it, is the following. So what we try to do is we have to construct this explicit isomorphism, and what we try to do is get a map from here to here, from the right hand side to M, which is likely to be an isomorphism, which is a good candidate for being an isomorphism. And how do I get such a map? Well, this is a direct sum, right? This is a direct sum, and therefore you can use the universal property of direct sum. So, for example, to get this map, it is enough for me to tell you what the map on this part is, and on each individual part, if I get a map, then I'll have a map from the direct sum to M. Now, of course, I have to choose that very carefully. From each individual part, I have to choose that very carefully in order that I will get an isomorphism, that this map, resulting map, is an isomorphism. Okay? Now, maybe you don't need to be very careful and the map will be an isomorphism, right? But if you, that may well be the case, but you may not be able to prove it. So, in order for the proof to go through, you would, there is a chance you might be able to do it if you choose these maps very carefully. Okay, so how do we choose these maps? So, for example, how do I choose Z mod? This from this to M, right? Okay. So the idea is to continue with this one, with this idea. So I choose a basis. Right? I choose a basis for this over PIM. Right? M1 to MS are a basis, right? And then I try to map. Okay. So here is a. So what you do is. Let's start from the beginning. Choose. What is this LR? LR is the dimension of, remember what this LR is. So let's write out LR. LR is dimension of PR minus 1M by PRM minus dimension of PRM by PR plus 1M. Okay, but PRM is 0. This is 0. Okay, so this LR is just dimension of PR minus 1M by PR. Okay, so what you can do is choose this M1 through MLR such that they are a basis of such that PR minus 1 M1, PR minus 1 MLR are a basis of PR minus 1m by P. You can do that. Okay, and then you can try to map. So you can try to map Z mod PRM to the LR to M by sending, there are, let's call standard basis E1, E through E LR, right? It's clear what I mean by this. So if there are LR components here, this one would have 1 for the first component and 0 elsewhere. This one would have 1 for the last component and 0 elsewhere, right? So you could map these respectively to M1. That's what I mean. I'm writing a bunch here and with this symbol. That means respectively you send a E1 to M1, ELR to M. Okay, so we can do this, no problem. Because, of course, in order to be able to do this, I must be able to send PR times this is 0, right? But that is true because PR kills the whole of M. Okay, that's no problem. Okay, so okay, this is how you start out. But then in the next step, there will be an issue. So what you would want is you would want M1, let's see, M1, M LR minus 1. Maybe I should call them some other names. So now let's see, MLR plus 1. MLR plus 1 plus LR, sorry, this is LR plus 1. Okay. Here it is MLR plus LR minus 1. Okay. The next LR minus 1 elements, how do I choose them? So I want, so this must somehow be the generators of Z mod PR minus 1Z to the LR minus 1. How do I choose these? Right? So you could try these to be such that P to the R minus 2 M LR plus 1 dot P to the R minus 2 M LR plus LR minus 1, okay, comma, okay. Now notice that when I multiply these by PR minus 1, they form a basis. But by our observation above, anytime you have linearly independent elements here, they are actually linearly independent elements in the step before. So if I do this PR minus 1 MLR, PR minus 1 M1, sorry, PR minus 2, PR minus 2 M1. Now these are linearly independent in this, in PR minus 2M by PR minus 1. Right? These are linearly independent because these are linearly independent in here. These are linearly independent in here. So that means these are linearly independent in here. Okay? These form a basis here. So these are linearly independent here. So I can, such that I can complete it to a basis here. That's what it means. Such that these form a basis for this. Okay. So the idea is if I take PR minus 2, that will form part of a basis for this. I complete it to a basis and I choose these elements such that when I multiply by PR minus 2, I get precisely that completion. Okay. Now, This is still not good enough, because you would want, so when you want to map this to LR minus, see, remember, you want to map, ideally you would want to map here some standard basis to these elements. Now that will require that PR minus 1 kills these elements, right? How am I sure that that's going to happen? Okay. So when I multiply by PR minus 1, so when I multiply by PR minus 2, they are in here, they are linearly independent. But I must make sure that when I multiply by PR minus 1, there is actually 0. But, okay, I can do that as follows. So I'll just say this. Okay. So can further arrange such that PR minus 1 of MLR plus 1 to PR minus 1 of MLR plus LR minus 1 is equal to 0. How do I do that? Okay, here is the idea. You multiply by PR minus 1. Right. Okay, maybe this thing is non-zero. Okay. But let's look at it in here. Right? You know that when I multiply by PR minus 1, these elements are a basis. So what you do is you look at PR minus 1, MLR plus 1, and write it as a linear combination of these basis elements. And then what you do is you modify your original choice of MLR plus 1 by a suitable linear combination of these elements, so that you can get 0. I hope that is clear. So your initial choice may be off the mark, but what you can do is you can modify. Remember that if I have a basis, and then if I modify the first basis element by a linear combination of the next few, it still remains a basis. So what I'm suggesting that you do is you take this element, modify it by an appropriate linear combination of these elements, such that when I multiply this one by PR minus, MLR plus 1, PR minus 1 power is 0. So, okay, and if you do that, then you can get these maps. Okay, of course you need to do this at every level, but it's clear once you see how to do it at one level, you can do it at every level. And then what you can show is that this map exists, and that this map is an isomorphism. So let's call this N. N is by definition this Z mod Pz to the L1 dot Z mod PRZ to the LR. And you have this candidate map to M. Okay, and what you can prove is that M mod PM is isomorphic to N mod PM. This phi, let me just continue to write this phi. Okay, this is induced by phi, but let me not, or if you want, you can put a bar, but let me not. Okay, and then Pn by P square N maps to Pm by P square M, and all these are isomorphisms, and so on. Okay, Pi minus 1M by Pim. There's a map through phi, and then this Pi minus 1M by Pim, etc. And once you know that all these maps are isomorphic, it's a very interesting exercise to show that the original phi is isomorphic. Okay, it's a simple exercise. Okay? So we do get, in fact, that this map is an isomorphism, and that finishes the proof of the structure theorem, right? And so modulo some maybe a few gaps, we have in fact completed the structure theorem for finite abelian groups, which we started out with. And I'm also out of time, so I should stop here. Thank you for your attention.
So today I would like to use the notion of group action to compute some numbers. So okay, so like say for example, so I indicated last time. Consider the group Z mod Bz let P be a prime number power n, and n is an integer greater than or equal to 1, and so call this as, so want to know so note that if note that if H contained in Z P power n is a subgroup, then H is isomorphic to Z P power n for some m which has this property 0 less than or equal to m less than or equal to n. So if m equal to 0, then it is the trivial group. H is the trivial group. That means it's just 0 element. And if m equal to n, then H has to be equal to the whole group. Okay. So in this case, there is exactly one such groups. Okay. So hence in these cases, so hence we can assume zero less than m less than n. Okay. And asked, so consider let S equal to set m, which is a subset of Z power P power n Z. M is a subgroup and M is, so if SM, M is isomorphic to Z P power M. So we would like to compute what is the cardinality of this, what is the cardinality of how many subgroups of Z power P power Z modulo P P Z to the power n subgroups which are isomorphic to Z P power m for some fixed m. Okay, so that's why I denoted it like that. So what is the cardinality of this? So this is meaning what is the cardinality? That is here for a set, if S is a set, this is by definition cardinality of S. Yes, that is number of elements in this set. Yes, okay, that's the question I would like to answer here. So I'm saying that using the group action, we can get a very nice answer to this question. Okay, so for that, I'll introduce some notations. Okay. So if first of all, look at automorphism of on P set power n. Okay. This is set of all f z p power n to itself. F is a surjective homomorphism. The same thing as once it is surjective, you can also see that because of the number of elements, it's also injective, and in fact, F is an isomorphism of abelian group. Homomorphism means once you have a homomorphism which is nice, is injective and surjective, then it has to be an automorphism. Such a thing is called an automorphism. Okay, and so this is set of all automorphisms of the group. So this is called the set of automorphism of the group ZPZ power n. So in fact, we can express this set of automorphisms in a very nice manner. Okay, so I'm saying look at Mn Zp power n is set of all f from Zp power n so I should write like this. E n to Z P n F is a group homomorphism. Okay. So any group homomorphism, so notice that this I can identify with set of all Aij 1 less than or equal to I less than or equal to j less than or equal to n that Aij belongs to Z. And we are looking at homomorphism which are surjective. So not Z p power n so is a subset of Mn Z p Z Okay? And in fact, we can identify this is equal to GLN Z PZ, which is by definition this set of all elements Aij in Mn Z PZ, such that determinant of, see, I am thinking of Aij as a matrix. I am saying that I can talk about determinant of Aij not equal to 0. Okay. So what is determinant of Aij? Because Aij's are elements in this Z mod PZ. It's a ring with P elements. In fact, it's a field. I am not going to use that. So I'm just going to use that. So what is the determinant of Aij? By definition, is if A equal to Aij, 1 less than or equal to I, j less than or equal to n, determinant of A, which is same thing as determinant of Aij, so is summation over all sigma in Sn. I'll say what is Sn. So sine of sigma, this is either plus or minus 1, A1 sigma 1, etc. An sigma n. This is A's are in Z mod PZ. So that product makes sense because Z mod PZ is a ring. Okay, so I can multiply elements, so I can make sense. So it is just this, where Sn is bijections of this set 1 to n, which I usually denote by P of this set. X is the set 1, 2, etc. n. Okay. And what is sigma of sine of a permutation? So sine of a permutation is defined like this. If sigma is a transpose, so let me just define this. Yep. So an element Sn is called a permutation of 1 to n. An element sigma in Sn is called a transposition if there exists Ij in 1 to n such that sigma k equal to k for all k not belongs to this Ij, this set consists of two elements, I not equal to j, and sigma takes I to j and j to I. So look at such bijections. So such a thing is called a transposition. Okay, and the fact that I am going to use is any permutation is product of transposition. See, last time I showed that if I take 1, 2 and 1, 3, okay, the composition gave me 1, 3, 2 or 1, 3 and 1, 2. I got the composition 1, 2, 3 like that, right? So that is for 3 element set. So similarly, you can show that any permutation can be written as product of transposition. Okay, so using that, we can define this sigma sine of sigma is equal to yeah, sine of the transposition if sigma is a transposition, then we define sine of sigma is equal to -1 and sine of the trivial element, sine of identity transformation, identity permutation, identity of 1 to this set n to be equal to 1 and sine of sigma 1 etc sigma n equal to sine of sigma 1 times sine of sigma n. Okay, so the fact, once I use this fact, any permutation is product of transposition, then it follows that for any sigma, I can express as product of transposition, okay, product of some finitely many transposition, and then sigma is the product of such this thing. That means signature is such a thing. Okay, so let's just consider the one example. N equal to 2, then what is out of z squared? This what I'm saying is can identify with equal to GL2 of Z mod Pz. So this consists of all matrices A11, A12, A21, A22 with so A111 identity permutation, that is A11, A22 and minus A12, A21. The other permutation with coming with negative sign, this is not equal to 0. That's the mean. So here I said that I can identify GLN of Z mod Pz with all these matrices such that their determinant is non-zero. Okay. Okay. So why we are considering this is, so giving a, what we are going to use is the following. In Raghavan's first lecture, we noticed that so look at Z mod P n, and so this is, we can think of as generated by n elements, namely Z mod. So this is Z mod Pz, direct sum, etc. Z mod Pz, n copies, an element. So I can think of as a row vector a11, a1, a2, etc. an belongs to Z mod Pz power n. Okay. But this I can write it as sigma ai, with ai is in Z mod Pz, ei equal to 1 to n, where ei is this vector 0, 1 at the ith place, 0 elsewhere. Okay. So any element I can express in this form. Okay. Now the thing that one is going to use is, if P Zn Zp Z n2 is a bijective homomorphism, that is an automorphism, then P of Ei will be some, I can write it as ai1, etc. ai, it's better to use the other way notation. a1i, etc. The first one is correct. A11, a1i, etc. ani. Okay. So then what is happening is, you look at this matrix 1 less than or equal to I less than or equal to. Then look at this. For each I, you look at this, and now you form the matrix A11, etc. A1n, an1, etc. an, and look at the action on this vector. Okay, so now I am taking the transpose of Ei, so 0, etc. 1 at the ith place. What do I get is A1 I, etc. AN I. So in other words, phi can be expressed in terms of this matrix. Okay? So giving phi is equivalent to giving the matrix. Aij 1 less than or equal to I, j less than or equal to n. And once you have this, phi's bijection is equivalent to saying that the determinant is non-zero. So that means I can have an inverse. So that's the condition. So that is what I use there. So that means, in fact, this belongs to GLN of Z mod Z. Okay. And let's look at what is the cardinality of this group. So note that GLN Z. See, I said that if you start with any set, so note that GLN Z mod is a subgroup of P of the bijections of the set P of Z over n. Okay, so and it's a subgroup because we are not allowing all the bijections. We are only allowing bijections which are preserving the group. So in particular, for example, 0 under any element of GLN PZ is fixed. Okay, so but in the bijections I can take 0 to anywhere. Okay, so this is a proper subgroup. GLN Z PZ is a proper subgroup of the set of bijections of Z mod P. Okay, this is, we don't require this, but what we are using is set of bijections. Look at set of bijections. In that, if you on the set, if you have more property, then you can ask all those bijections which preserves that property. So in other words, so for example, what we are saying is that the set has an extra structure, namely it is a group and we can consider set of bijections which preserves the group structure. Okay, so that's what, then we get a subgroup. So in this special case, okay, what we are getting is GLN of Z mod PZ. Okay, this is special group. So for example, meaning if you take, if x equal to R2, and so this is a vector space. Now if you look at GL2R, so this is set of all F in bijections of R2, such that F is linear. That means F is R linear. So this is a subgroup of set of all bijections of R2. See, R2 is set of all bijections is a very big group. Okay, so for example, I can take translation by an element of R2. So that's also a bijection, but such an element is not there in GL2 of R. Okay, GL2 for R consists only of, I can identify with all those 2 by 2 matrices whose determinant is non-zero. Okay, so this is just a aside, an example. That's what I'm saying. So what we are doing is the same kind of thing for the finite group Z mod PZ power n. Okay? Yeah. Okay. So let's look at what is the cardinality of GLN Z PZ. Okay. So this is, we can check that this is, how do we get such a thing? So what is the meaning of this? So first you choose any non-zero element. So first look at A11, A1n, AN1, etc. ANN belongs to GL N ZPZ, implies first A11, A1n is non-zero. Okay, so that means I can choose any of the element. I can this thing. So this belongs to Z P Z power n minus the element 0, 0, 0. Okay, so that means I can choose for the first element of the matrix, n by n matrix with coefficients in this finite ring Z mod PZ. I can choose any element. So that means there are p to the power n minus 1 choices are there. For A11, etc., A1n. Okay. Now, if I choose the first one, okay, the second one should not be a multiple of the first one. Okay, if it is a multiple, then what happens is they become, meaning the subgroup generated by first and the second will be the is same as Z mod PZ. It's isomorphic to Z mod PZ. Meaning when I try to compute the matrix, the determinant of the matrix, the determinant becomes 0. Okay, so next one, A21, etc. This vector A2n should not belongs to. We take the subspace generated by, or subgroup generated by ZP which are consists of multiples of A11, etc. A1, N. Okay. So this has P elements. Okay. So I should not have this. If I have this, I will not get the determinant non-zero condition. Okay. So I can choose anything which is other than this. So that means I have choices for A2 1, etc. A2 N can be chosen in p to the power n minus p base. Once first one is chosen, the second one, there are so many choices. It should not be the multiple of the first one. Okay, so there are these many choices. So similarly, if it is so, etc., you will see that a n1, etc. I will write a I ni has can be chosen in p to the power n minus p to the power. So I should have written the other way. I1, etc. In can be chosen I minus 1 base. Okay. And if I continue like this, so a n1, etc. a n n, the number of choices can be chosen in p to the power n minus p to the power n minus 1. Once the choices of a11, a1n, an minus 1, 1, an minus 1, n are made. So similarly, I should say here. So there are these things for A221. Once can be chosen way. Once the choice of A11, etc. A1n is made. Okay. So similarly, I should write here also. Once, so here base, once the choice of A11, etc. A1n, I have already chosen this I minus 1, 1, etc. A I minus 1, n. If I have chosen these things, the remaining choices with this successive way of choosing, once I choose this, then there are p to the power n minus I minus 1 choices. So in other words, what we are saying is the cardinality of this GLN Z mod Z is p to the power n minus 1 into p to the power n minus p, etc. p to the power n minus p to the power n minus 1. So let's look at the example. GL2 of Z mod Pz. What we are saying is that consists of A11, A12, A21, A22, such that A11, A22 minus A12, A22, 21. This is not equal to 0. That means these two, the first row is not a multiple of the second row, or second row is not a multiple of the first row. Okay, so that's what we are assuming. This is so the first row we have p squared choices, but I cannot take 0, so I have p squared minus 1 choice. And once I choose the first one, I have, for the next one, I have p squared minus p choice. Okay. So this is the number of elements in equal to the number of elements in GL2 Z mod Pz. So similarly, p cubed minus 1, p cubed minus p cubed minus p squared. This is the number of cardinality of GL3 of Z mod Pz. Okay. Yeah. So then, now what I want to use this following. So now I am. So we will first we have computed the order of this group. GLN of P is GLN of Z mod Pz. That is same thing as automorphism of Z mod Pz over N. So this is what we have computed, its order. And so our original problem was Sm 0 less than m less than n, and we are looking at Sn set of all m contained in Z Pz power n, such that m is isomorphic to Z mod Pz power. Okay. So yeah, so claim is that the group, the automorphism group, the group of Z mod Pz over n, that is we have identified with GLN of Z mod Pz, acts on Sm. Okay. So what is the action? So in other words, I have to define an action of this thing. So GLN Z mod Pz cross Sm to Sm. I have to define a map. So what do I do? So see, I'm thinking M the subgroup in Z mod Z n. So in fact, M can be thought of as generated by M elements V1, etc. Vm, where V1 not equal to 0, V2 does not belongs to the subspace generated by V1, and V3 does not belongs to V1, V2, the subspace generated by V1, V2, etc. Vm does not belongs to the subspace generated by V1, etc. Vn minus 1, or the subgroup generated by V1, etc. Vm minus 1. See, subgroup generated by, given an element, the subgroup generated by that is just all the multiples of that element. In this case, multiple means elements of Z mod Pz. Okay, all the V type lambda times V1, where lambda is in Z mod Pz. Okay, and here the subgroup generated by V1, V2 means it consists of all AV1 plus BV2, where A and B belongs to Z mod Pz. Similarly, the subgroup generated by V1, Vm minus 1, okay, is consists of A1, V1, etc., AM, Vm, where AIs are in Z mod Pz. Okay, and the assumption that M is in M belongs to Sm means I can always find V1, etc., Vm such elements, because what is the assumption on M? M is isomorphic to Z mod Pz power M. So now look at in Z mod Pz power M, I have Ei 1 less than or equal to I less than or equal to M. So look at its images in M. They satisfies this property. Okay, take any one of them and take any isomorphism psi. Okay, fix an isomorphism, then it satisfies such a property. Okay, so this way now I have the MS like this. So now I have, yeah. So now A11, etc. If A is equal to Aj belongs to GLN, then we can talk about A of V1, etc. A of Vm. I'm thinking of V1, etc. Vm as column vector, A as a matrix. I can apply it and get again a subspace which is isomorphic to, or subgroup which is isomorphic to this subgroup is isomorphic to Z mod P Z power M. Okay. So this way, so M going to A comma M. If M is V1, etc. Vm, so the subgroup that I am going to get in Sm, if I start with M and take A, the subgroup is A1, etc. A So I get an action like this. Okay. Claim is that GLN Z mod Pz acts transitively on this SM. Okay. So that is easy. What happens is, so take M1 and M2. So M1 is given by V1 etc. Vm, and yeah, if M1 is equal to V1 etc. Vm and M2 equal to W1 etc. Wm, then so you extend, we can extend find V1 Vm plus 1 etc. Vn such that V1 etc. Vm plus 1 etc. Vn. This is whole of Z mod Pzn, and similarly if I start with W1 etc. Wm, I can extend it to Wm plus 1 etc. Wn, such that this is also the subgroup generated by these n elements is also same. Then I can express V1 etc. Vm in terms of the elements W1 etc. Wn, or vice versa. So if phi is the matrix, corresponding to the bijection Vi going to the Wm and less than equal to less than n. Okay. Then we see that phi of M1 equal to, okay. So in other words, what we have shown is that Sm acts transitive, acted transitively by the group GLN of Z mod Pz. Okay. So now if I use the properties of the transitive action, so let's look at things. So let if a group G acts on a set X transitively, then X can be identified with with the coset space. With the coset space. G mod Gx, where x in X and Gx is the stabilizer or isotropic group. Group. In other words, what we are saying is X becomes the orbit of X under the group G, and the orbit of X, the isotropy is the element which fixes X, all those elements in G which fixes X, Gx equal to X. Okay. And now you have the coset space G by Gx. Okay. And we can identify X with the orbit space, orbit of X under X, the orbit of X under the action of G, so OX. Okay, so X can be identified with that. So in other words, what we are saying is the cardinality of X can be is equal to the cardinality of this coset space. So this implies cardinality of G by Gx is equal to cardinality of OX, but cardinality of G by Gx is nothing but cardinality of G divided by cardinality of Gx. Okay. So now if we apply this principle in the previous problem, so now what we have said was Sm I can identify with some GLN or GLNZ Pz mod G M, where M contained in Sm. So look at its isotropy sub. Okay. So and also it is this coordinate is so I can choose any element in Sm and find out what is Gm. That is enough. One element, if I for the one element in Sm, if I find out what is its cardinality, that will give me the cardinality of this. So for example, look at M equal to, if M equal to the subspace generated by 1 etc. E M. Okay, then we can check that Gm is conserved all A in GLN such that GLNZ see is that. So it is of this form. See, every element takes E1 etc. En to itself. So that means when I write the in terms of the matrix, what it says is that it will be of this form: A1 0 B1 C. Okay, where A1 belongs to GL M Z mod Z, and B1 belongs to GL N minus M Z mod Z, and C belongs to C belongs to, I will write the matrices M, M, M minus N. Okay. So this is consists of all Cij 1 less than or equal to I less than or equal to M. But yeah, and J is 1 less than or equal to J less than or equal to M minus N. And Cij arbitrary elements in Z mod Z. Okay. So the cardinality of M N minus N is P power, because there are M into M minus N. So it is P power M into M minus N. This is the cardinality of this set of elements of the form C is of that cardinality. So I want to compute the cardinality of GM. Cardinality of A is, I know that. So cardinality of A is P M minus 1, etc. P M P M minus 1. Okay. Similarly, cardinality of this is cardinality of GL M Z mod Pz is this. Cardinality of GL M minus N minus M Z mod Pz. It has cardinality P to the power M minus N minus 1, etc. P to the power M minus N minus P to the power M minus N minus 1 as this cardinality. So in other words, what we get is, so if you compute this thing, so therefore cardinality of GM is the product of these three cardinalities. So that means it is P power M minus 1, etc. P power M is P power M minus 1, etc. P power M minus N minus 1, etc. P power M minus N minus 1, and then this is here P power M minus N minus that. Okay, and then the cardinality of the matrices of type C. Okay, so that is what we said is P power M into N minus M. Should be N minus. M is smaller than N. Okay, so N minus M. P power M into N minus N. So this will say that the cardinality of, so this implies hence the cardinality of Sm is equal to cardinality of GLN Z Pset modulo cardinality of GM. That's what we have said. So this is equal to, we know the cardinality of this one, p power n minus 1, etc. p power n minus 1 divided by p power m into n minus m and p power m minus 1, m minus 1, etc. p power m minus p power m minus 1, etc. p power n minus m minus 1, p power n minus m minus p power n minus m minus 1. So this is the cardinality of Sm. So I'll stop here. So if there are questions, I will take it. Otherwise, so we can stop.
Okay.
Okay, thank you.
In this last lecture, I will recall the question that I posed at the end of my previous lecture. Okay, so we saw instances of a situation where you have this, of course, exponential map. Exponential map was defined from here to GLN R and also exponential MNC to GLNC. Okay, and we saw that if you take this is, let me just state the question first. So suppose that V a subspace of Mn, so n cross n matrices over reals or complex MNC vector subspace, okay, is a vector subspace, the real or complex, complex vector subspace is exponential of V, which is of course contained in GLNR or GLNC. See, so it's a subspace. The question is it a subgroup? Is this a subgroup? This is a question, and I said that the answer is no in general. I'm just recalling what I stated towards the end. Answer is no in general. Yes. So let me write it in a different color. Yes, if V is a Lie algebra, Lie subalgebra of, well, Mn or MNC. That is, so what's a Lie algebra or Lie? So what is, first of all, MNR is a Lie algebra. So let me just say that. So I continue. If x and y are in Mn of R. Let me just stick to Mn of R, matrices with real entries. Then this denotes Lie bracket is xy matrix multiplication minus yx. Okay, so this is a definition of the Lie bracket. Okay, so V is a V vector space is a Lie algebra. It's a Lie subalgebra of Mn R if xy in V implies that the Lie bracket of xy is actually in V. Okay, so this is a condition, and so if this condition, so I already commented about examples, but let me just work out explicitly one example. So one or two examples maybe. So V is equal to space of all trace 0. This I stated at the end of last lecture. Sorry, this must be written as Mn of R. So here R or C. Okay, let me write R here just for definiteness sake, such that trace of x is equal to 0. And why is that? Why is it that in this case V is a Lie subalgebra of this? So we have to check that. So if x and y are in V, then we know that trace of xy, trace of x equals 0, and that's also equal to trace of y. And now we verify what about trace of xy. Actually, it doesn't really matter. If you take any two matrices, n by n matrices, you compute the receiving trace. This is equal to trace of xy minus trace of yx, and that's trace of xy minus trace of xy minus trace of yx, linearity, and this is trace of xy minus trace of yx is same as trace of xy, so trace of xy which is equal to 0. Okay, so therefore by the defining property of V, xy, Lie bracket xy is also in V, and we already saw that. In fact, so we already saw that exponential of this V. So in this, so I should erase this dot. Okay, so exponential of V is in fact SLN determinant 1 matrices. Okay, in this case, so this is the first example. Yeah, let us do the next example. I stated this also last time. Okay, so V this time is space of all skew symmetric matrices X in Mn. You can either work with real or complex, it would not matter. So skew symmetric matrices, that means X transpose is minus of X in symbols. So now suppose that, so this is a question we want to ask. Suppose, so we want to verify whether V is actually a Lie algebra with respect to this bracket operation. What can you say? So that, yeah, you know, X transpose is equal to minus X, Y transpose is minus Y. Okay, what about Lie bracket XY transpose? What is this? Well, definition of Lie bracket tells me it is xy minus yx transpose, and that's equal to, well, transpose distributes over addition, so it is xy transpose minus yx transpose, and this is equal to, well, y transpose x transpose minus x transpose y transpose. This is how you get it. But y transpose is minus y, x transpose is minus x, so this is yx minus xy. But this is exactly the negative of the Lie bracket of xy. Okay, so therefore again V is a Lie algebra under bracket. Lie algebra under bracket. Okay, that is it's a Lie subalgebra, and we already saw that exponential of V is equal to yeah, so actually so SON. Okay, so do you recall the proof of this? See, this is because X transpose. So okay, let me just briefly give an explanation why this is so. So you, if you take an X in V, what we get is X transpose is minus X. In particular, X transpose and X transpose and X commute. So I just verify this. This is equal to X transpose. This is same thing as e power X plus X transpose, because X transpose and X commute. Because X transpose is nothing but minus X. But this says that this is e power 0 is equal to identity. And so in particular, e power X is an orthogonal matrix. Okay. But determinant of e power X is e power trace of X. So X being orthogonal, e power trace is 0. In any case, determinant is of course positive, and it's an orthogonal matrix, and therefore determinant equal to 1. Therefore, this is contained in here. And in fact, it's equal to, and let me give a quick explanation for that. So suppose that A is an orthogonal matrix. So A is in SON. Well, then, so I probably mentioned this last time. There exists a matrix. There exists a P. In fact, again in orthogonal matrix SON, such that so P A P transpose. So that's same thing as P inverse anyway. So this is looking like 2 by 2 diagonal blocks. So this requires a little bit of linear algebra. I'm not going to do this. If you work over complex numbers, it's much easier. Then you will get unitary group, and any unitary matrix, you can put it in the diagonal form. Here you cannot put it in diagonal form, but you can put it in 2 by 2 block. This is RT1. I think I probably said it, RTTN, TM, and then there is a 1 by 1 block that is either present or not present, depending on whether n is equal to 2m or 2m plus 1. So depending on that, this, so here let me underline by this and write it in green color. Okay, so this additional bit will come only if it is of that nature. Okay, so once you, how does this help us? Then you see that, we know these 2 by 2 blocks, they can be realized by corresponding. So I just very quickly say that take X to be equal to minus T1 minus T1, this matrix 2 by 2 blocks, blah blah blah, and the last block is Tn minus Tn, and if n is odd, you stick in extra 1, in extra 0 here in this in this 1 0. Now by sight you can see that this is in fact skew symmetric and therefore belongs to V. And you compute e power x, and that's equal to PAP inverse. And that follows that. So if you take P x P inverse, this you can, yeah, so take e power of this, that's equal to A. But notice that PAP inverse is same thing as PAP transpose. Okay, sorry, X, I wanted to write X here, P transpose, yeah. So now look at, so I want to see that this is actually skew symmetric, but you just take transpose of this. I hope it's clear what I wrote here. Let me not scribble. P X P transpose. And now take a transpose of this. P X P inverse transpose is going to be, so you write the transposes in the reverse. So P transpose is P X transpose P transpose, but that's same thing as, let me squeeze that in, X transpose is minus X. So P, again P transpose is P inverse. Okay, so this is in fact, so that shows that this is this matrix is again in skew symmetric matrices. The notation I used was skew n. Okay, so in fact this map is therefore onto also. Okay, so that proves this equality. This explanation proves equality. That I hope that's clear. Okay. Why did I say that P transpose is P inverse? That's because of this condition here. I am using that. See, there exists in fact an orthogonal matrix. Okay, so special orthogonal matrix, so that PAP inverse is actually this. Okay, so all this goes on to show that, well, in fact, a little more is true. I will not elaborate on this. You can talk about dimension of these groups, because these groups are also manifolds, and the dimension can be read off from the dimension of the corresponding vector space. Mind you, exponential map is a local diffeomorphism, so the dimension of V will be same as the dimension of the group it maps to, in the case when V is this one. So this allows us to actually compute what is a dimension of the orthogonal matrix. So as a consequence, or as a corollary, dimension of the orthogonal matrix, okay, special orthogonal matrix, is same thing as the vector space dimension of skew symmetric matrices. But this is easy to count, because for a skew symmetric matrix, along the diagonals you have 0, and whatever you have here, you have negative of that. Okay, and upper triangular entries can be arbitrarily filled in, so that are n choose 2 choices. So n choose 2, that's a dimension. And likewise, you can compute what is the dimension of the special linear group SLNR, and this is in fact equal to, well, trace 0 matrices, trace 0 condition, so dimension of trace 0. And I used this notation there last time. So this is equal to, the whole thing will be n square, and trace is a linear functional. Kernel of the linear functional will be n square minus 1 dimension. Okay. In fact, kernel is 1 dimensional, therefore the dimension of the space, vector space is, kernel is actually, sorry, kernel is n square minus 1 dimensional. Yeah, so it's a linear functional. So okay, so that's also the dimension. All right, you can do the analogs for skew Hermitian and so on. and you do the count, and then I will simply write here dimension of the unitary group Un is in fact equal to n square. So this is not complex dimension, but this is real dimension. So this is, remember, dimension of or R of the what is that? Yeah, so skew Hermitian matrices. Okay, I think I use this notation. It's a temporary notation. So just let me write here skew Hermitian matrices. And you know what is the dimension? How do you compute the dimension of skew Hermitian matrices? It's so up here you can put arbitrary complex numbers, and along the diagonal you should have purely imaginary numbers. Okay, ixn, and whatever number you have here, you put conjugate and then put a negative here. This is how a typical skew Hermitian matrix looks like. The star here is actually a complex number, so belongs to C. And now you can count the real dimension. How many choices are there for the star? There are n choose 2 complex choices, and therefore real choices will be this. So that is 2 times n minus 1 divided by 2. The 2 goes away, so I get n times n minus 1. Okay, and but then along the diagonal purely imaginary, so therefore you must add n more to it to get the real dimension, and that gives me actually n square. So this is the explanation. Okay, so I had some more things to say. I realize don't have much time. What about this question naturally arises? What about symmetric matrices? Over reals are complex numbers, so let's just say over reals. Is this a Lie algebra? So Lie subalgebra of Mn of R. So let's just call this maybe symmetric, temporary notation. This is the space of all symmetric matrices contained in Mn of R. Now you take two symmetric matrices A and B, symmetric matrices. That means that A transpose is A, B transpose is B, and now you compute you see you want to check whether AB transpose again belongs to, again is a symmetric matrix, only then it will belong here. It turns out that this is, of course, you can simplify it. This is AB minus B, exactly as we did in the case of skew symmetric. You carry out the computation, but you see something happening. This will become B transpose A transpose minus A transpose B transpose. Yeah, so that's equal to, okay, so what did I do? AB minus BA transpose. This is B transpose is B. A little puzzled that time. AB transpose is AB transpose becomes B transpose A transpose minus BA transpose. Okay, this is BA. Surprisingly, minus AB. I didn't expect that. Should not be a Lie algebra. A minus I'm a bit surprised. Something I'm not doing right, I think. AB. Yes. Okay, fine. No problem. Okay. What are we supposed to get? We are supposed to, so, but this is equal to minus of A comma B. Okay, so not equal to AB. See, we want to check what? We want to know whether this is symmetric or not. Okay, that's our question. Symmetric? It is not symmetric. In fact, it is skew symmetric. Okay, so not symmetric unless of course A and B commute. Not symmetric if A and B, if AB not equal to B. Yeah, no problem. So you can check that. Okay, so I take a certain matrix. Of course, this is not a proof. See, this only says that this implies what? This implies that this space of symmetric matrices is not a Lie algebra. Because you can find this 2 by 2 matrices which are symmetric but non-commuting. Okay, so it's very simple. I can give you an example, but I let you play with it and find out. You can take, in fact, one of them to be even diagonal. You take 2, 3. Actually, you can just choose randomly almost anything and it works. So you can write here 2, 3, and then maybe I just write something here. 1, 1. You can check that this is not going to be equal to, this is not equal to, just check this 2, 1, 1, 3. You can choose almost at random. It's not going to work out. Okay. So this is not a Lie algebra, therefore. Okay. Now, but that's no proof that the image is whatever. The image could very well have been the group. I mean, a group. How do you know? So one can compute the images of these matrices and then show that they are not symmetric. Okay. The product again is not symmetric. I want to say the following thing. So here is an important, yeah. So first of all, I want to say fact. So suppose that A is a symmetric matrix. So symmetric matrix with in Mn of R. Okay. All right. The image may not be a group, but it has an interesting property. So what can we say about what type of a matrix is this? This we know is, of course, symmetric. Yeah, we already know that. But it has an additional important property, symmetric. The important property I want to write in some other color, positive definite. Positive definite matrix. Okay, and I'll give a very a brief proof of this after I tell you what is the definition of a positive definite matrix. Okay, so what is a positive definite matrix? So recall, we say that a matrix, yeah, symmetric matrix, matrix over reals is positive definite if, okay, for any x in Rn thought of as a column vector, you look at this. So I didn't give a name, so any matrix B, x transpose B x. Notice that this is a 1 by 1 matrix and therefore it can be thought of as a real number. Yes, so this is positive So for all x, this must be positive. If x not equal to 0. Of course, if x is 0, then it's 0. So this is the definition of a positive matrix. And how do we show that when you take a symmetric matrix A and take let us call this equal to B, okay? So how do we say that B, which is equal to e power A, is positive definite? All right. Now again, I'm going to make use of the following property. If A is A in Mn of R is symmetric, then there exists, in fact, an orthogonal matrix. Let me write that orthogonal matrix P, and you can choose it to be SON, such that, okay, P inverse is diagonal lambda n in Mn of R. In other words, all the eigenvalues are real. In fact, A is diagonalizable. It has a basis consisting of eigenvectors in R power n, which are in fact orthonormal, which form an ON basis. This is a basic fact proved in linear algebra course, so I recollect that fact. And then this is just an interpretation of the same fact. Okay, now we can compute e power P inverse. This is equal to, well, on the one hand, this is P e power A P inverse. This is equal to this. How am I doing in terms of time? I have half an hour. Okay, but this is a diagonal matrix, so you can write this P lambda 1, blah, 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 e power lambda n. Okay, and all the diagonal entries are positive. This matrix, this is evidently positive definite, symmetric and positive definite. Symmetric is obvious because it's diagonal, and once all the diagonal entries are positive, this is positive definite. Okay. And now how is this related to this? So this is PB inverse. This is, so P e power A P inverse is same as this, but this is same as P transpose. Okay, now you can compute for any x the following. So if x is in R power n, okay, you want to look at x transpose, yeah, B x, and you wanted to show this is positive. Okay, so what you do is you replace, put y is equal to px and do the calculation. Of course, this is a bijective correspondence, so if you check for such vectors, then it is equivalent to checking for anything. Okay, so now this becomes, sorry, so I will write instead of this, no, okay, maybe I just write here P inverse, maybe that's okay. But P inverse is same as P transpose, so I write P transpose X. And now compute this. Yeah, so yeah, let me just write this here instead of this, make this equal to y, it's much easier that way. Okay, y transpose. Okay, so this is equal to just substitute for y is equal to P transpose yeah, so I need not have written this. Let me erase this. Okay, fine, no problem. So what is Y transpose? Y transpose is X transpose P transpose. Remember that. Okay. Maybe I want the transpose on this side, so I do have to put transpose here. Sorry about that. It requires a bit of experimentation. So the transpose goes away. All right. Then Y transpose X becomes X transpose P B, and Y is P transpose X. But this is just a diagonal matrix with positive diagonal entries. X transpose this diagonal matrix. Okay, let me write that as e power lambda 1. All right, e power. So anyway, this is positive definitely. See, e power lambda n times x. And if x had, if x was column matrix x1 blah 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 xn, then this can be simplified. You substitute that in here, what you get is summation e power lambda j xj square, j going from 1 to n. But this is of course greater than or equal to 0, and equality holds only if x equals 0. Okay, so this is a positive definite matrix. Okay, so what we have shown is the following. And also conversely, let me say this. Yeah. So let me summarize whatever we did just now. If A is symmetric, this is what we proved. Then B is equal to e power A is positive definite. Okay. Converse is also true. Again, by the same logic, you can just reverse a step essentially. Conversely, if B equal to B is symmetric and positive definite. Okay, first of all, symmetric would mean that you can diagonalize it using an orthonormal transformation. There exists a matrix P. I'll this time use Q. I suppose I can use Q. So there exists a Q in SON such that QA, QB, Q transpose or Q inverse both mean one and the same. Okay, is equal to diagonal. And diagonal, we will just write it as some B1, blah, 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 Bn. But positive definite, see, this positive definiteness of B implies that Bj are all positive. Moment Bj are all positive, you can find some lambda 1, lambda 2, so that this can be written as e power lambda 1, e power lambda n. And now you do the unwinding. So this is all that you need to observe, where e power, so you can write what lambda is. Lambda j is equal to log bj. Okay, and once you do that, now you just take it to the other side. B is equal to q inverse this matrix. Let me just write e power capital lambda, self-explanatory notation. Q transpose is Q, but this is same thing as e power Q inverse, but now Q inverse is same as Q transpose lambda Q, and this is symmetric. So symmetric. Okay, so therefore what we have shown, in fact you get a unique matrix this way. Okay, so what we have so what we have shown is the following: symmetric matrices map to under exponentiation, positive definite. Positive definiteness already subsumes symmetry. So, okay, all right. So this is what, and in fact, you can show with a little more care, you can show that this is a bijective correspondence. Okay, but symmetric matrices as a topology, and that way you can say, well, it inherits a topology. But anyway, this is sub of GL, and okay, so already there is a subspace topology here. This is a vector space, and in fact, this restriction of exponentiation is in fact a continuous map, and so you can say it's a homeomorphism. All right, it's a homeomorphism. You can, if you want to care about differentiability, you can say it's a diffeomorphism. That statement is also valid. Anyway, so we have this continuous bijection with inverse also being continuous. Now, what I want to say is the following. This is something which is really a very important property. Now, if you take SLN R, okay, and so let me write this. So theorem, this comes out of these whatever observation I have already made with a little more work. Any x in this one can be expressed uniquely as x is equal to some k times exponential a, where k is a rotation matrix, k is in SON, and a is positive definite. A is symmetric. A is in symmetric. And slightly stronger statement. This is a weaker statement. The stronger version is that I have a map. This decomposition is unique. This decomposition is unique. In fact, so you write this decomposition as ln of R. I can just send it to k cross exponential of the symmetric matrices. So that's a notation. So this, I don't like to write k, it's actually SON. Yeah, SON. Sorry, this n is not properly visible. And cross this. So x going to, either way you can write k cross exponential k times, okay, k, well, you can write k comma if you like, k comma exponential of a. After you decompose this, okay, is a diffeomorphism. Okay. Diffeomorphism. All right. So I in other words, this you should I explain this? Just one familiar context in which you have this type of decomposition. You see, what we are saying is any matrix can be written as a special orthogonal matrix. Any matrix of determinant 1, special orthogonal times a positive definite matrix. Okay, and this decomposition into k and exponential of a is unique. All right. So let me say this may seem a little bit mysterious to you why it is so, but we usually give as an exercise for students studying BSc, maybe linear algebra, any matrix X in Mn of R can be expressed uniquely as x is equal to skew symmetric So x minus x transpose by 2 plus x transpose by 2. Okay. So this is happening at the level of Lie algebra. You see, skew symmetric matrices that formed a Lie subalgebra. This is okay. So, and this symmetric matrix. So, and this expression is unique. This is usually an exercise for BSc students. You may have given this exercise to the students several times. But what this above theorem says is that this happens, this has deep implications. And what is that implication? Any matrix with the determinant equal to 1. By the way, if x is having trace equal to 0, okay, if x has trace equal to 0, then of course this has trace equal to 0, this also will have trace equal to 0. So in that case, yeah, so you have this decomposition. This decomposition that you see here is a shadow of this, in fact, a more refined and deep implication coming. I don't know which one is a shadow. Maybe I should say this is a shadow, but this is exactly what is the implication. Okay. I wanted to also say one other application. Most of my application have been so far to either groups or to linear algebra. But there is one other application. I will be very brief about this. Unfortunately, I don't have time to elaborate on this. So this one is solving differential equations. Of what kind? Of the following kind. Okay. So linear, yeah. So suppose that x is a vector, but it's a curve, so it depends on t. Xt is a vector in Rn, and the t you can think varies in real numbers. Okay, so it's a smooth curve if you want, or you can say, okay, let me write this. So this xt, you write it as a column. Okay, x1t like this, xnt, and write transpose. Sorry for the abuse of notation, but this notation is common, t for transpose and also t for time. Then what is x dash of t? Already I mentioned this, you just differentiate each of the components. X1 dash t, dash denotes the derivative with respect to time, xn dash t. And what is the type of differential equation which you are interested in solving? So x dash of t is equal to some matrix times x of t. Yeah, so this is a differential equation. Let us see, give a simple example. So, okay, so x1 dash of t is equal to, so when this is, let us say 2 by 2 matrix example, 2 by 2 matrix, this could, A could be, take A to be equal to something, 2, 1, 1, 1, all right. So 2 x1t plus x2t and x2 prime t is equal to x2t plus x1t rather, this column x1t plus x2t. Okay, question is how to find solutions of this, and what can you say about the space of solutions? Erase this and try it properly. Okay, maybe some of you have already seen this. So the thing is, we proved this. I will first state the theorem. Okay, I would have elaborated on it a little more, but for want of time, I have to be brief. Okay. So I'll state the theorem first. Theorem. The system of differential equations. So here, let me emphasize this. We want to have constant coefficients. You can make A to have coefficients depending on this, but I don't want to consider that. A is in Mn of R. Okay. For example, I could have written here instead of 2, 1, 1, 1, I could have written 2x1 and then maybe cos x1, x2 and then sine e power x, x1, x2, all kinds of things. I could have, matrix A could have been matrix of functions again. Functions in what? Functions in the coordinates of R2. But no, we are only working with constant coefficient matrix. That is, matrix A has constant, this entries coming from real numbers. Okay. Then the system of equations. So x prime t, briefly written as x prime t, is equal to axt has solution space equal to the column span of the matrix e power a. E power t times a. Yeah, say solution must be functions of t. All right. So let us give a quick proof of this. So how do we prove this? Recall d by dt of e power ta. This is equal to a e power ta. Correct? So, but you see, what is e power ta? That's so yeah. So first of all, you write e power ta, right? E power ta as well in terms of columns, right? x1t, blah blah blah, xnt. This x1 should not be confused with the variables. Otherwise, there will be confusion. So here, yeah, there will be confusion if I write like this. Let me write here. Okay, I will write not in this notation. We will, of course, stick to this notation in a minute, but there is a double thing going on. So let me write it as xij t. Very simple. Okay, let me write it like this. Then what is the column of this? Okay, so if this is the case, first of all, let's just write this. Then what is the meaning of then d by dt of e power ta, I should have written it in the next page. This is equal to, well, you just take the derivative with respect to time of the matrix entries. This is a definition after all. So what is the jth column of this? Yeah, so let's see. What this is saying is, so I have this, mind you. So what we have is that the jth column would look like, let's just look at the first column. Okay, first column means I am putting here 1 1 t x prime 1 n t Okay, first column. This is same thing as A times the first column on the right hand side. That's again x11t, x11 prime t, blah blah blah, x1n prime t. Okay. Is this clear? Just if you have equality of matrices, see you have this matrix equation. Now this is an n by n matrix. This A, you keep it as such. You have, how will you compute the product of this matrix? You look at the jth column and then multiply by A. I will get a jth column of this product matrix, right? So this equation is equivalent to saying this, and now I will put here. I think I made a mistake here. One, it should be n here. Sorry about that, because I'm fixing the column. Column index is, sorry about that. I was in a hurry to wind up. So here j, and here this is j, and this is j, and n. I'm fixing my n. So this is n. Okay, this is what I have. All right. So that means that this implies that the jth column satisfies the equation xj prime. So satisfies the equation x prime t is equal to a times xt. Okay. Now the columns, see the columns of this matrix are all linearly independent because it arises as an exponential of something, and therefore you get n linearly independent solution. And it's just a little more work to show that these linearly independent solutions you can take. Now you see, the because matrix multiplication is the multiplication by A as an operation is linear. The moment I have, so you can say that here. So if AT and BT are solutions, then so are C of AT and some AT plus BT. So it's the space of solutions actually is a vector space. That's what it says. And you have, it's not difficult to show. I just that I don't have time. I initially planned on showing, but I don't have the time to show that these actually give you the full set of the column span. That is any solution. Any solution of x prime t is equal to a times xt is a linear combination. Is a linear combination of the, so the jth. So I need a notation for the jth column. It may be confusing. I will write this to be, so sorry, I should not have put prime here. I noticed I was in too much of a hurry, so there should be no prime. There is no differentiation on this side. So let us call this Vj, just so that you understand what I am talking about. This is then V prime t, so j. Okay, so the solutions are any linear combination. Any solution of this is a linear combination. Let me write that linear combination. C1 V1t plus blah 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 plus Cn Vnt. This is exactly the same thing as saying that the column span will be a vector space. Column span is the space of solutions of the given differential equation. I wanted to illustrate this and so on. For want of time, I should stop here. Okay, now before I conclude, I have this pleasant duty of thanking so many people who helped me organize this. So let me just mention that. First of all, I thank the resource persons, Professor Nagaraj and Professor Raghavan, for readily agreeing to give these lectures in spite of their busy schedule. They are all extremely busy people, and we are so grateful to them that they could find time to give talks in this lecture series. I should thank Indian Academy of Sciences for providing financial support to run this workshop. I would like to thank Mrs. Srimati, Executive Editor of the Proceddings-Mathematical Sciences, for helping me organize this program. I thank Ms. Soumya and Mr. Sumesh at Indian Academy of Sciences, and Dr. Varuni Prabhakar, Outdoor Coordinator at Institute of Mathematical Sciences, for providing all the technical support. And last but not the least, I thank you all the participants for patiently listening to our lectures. And this meeting is concluded. Thank you all.